Okay, I think that's mainly it, so we'll get going. Thanks for joining us this morning for this webinar on math functions. It's relatively short video this morning. It's about 15 minutes, and if you have any questions throughout, please put them into the questions panel, and we'll get to them at the end. So let's get going.
Welcome to today's demonstration. We will be discussing math functions in the Horner OCS all-in-one controllers. Let's get started. So today we're looking at our advanced math operations and our conversion operations. So I've dropped an add block on the screen here, and we'll discuss what type of variables we're doing math on. It's important that all the functions match. For example, if you're doing a calculation on integers, then all the operands and the result all need to be integers. With integer math, all of our values have to be plus or minus 32,767. We've also got unsigned integers, where the values are going to be positive only between 0 and 65,535. We have double integer values that are 32 bits wide and are positive or negative. They take up 2 consecutive registers in the register-based math. Unsigned double integers are 0 up to very large numbers. They're also 32 bits wide and are positive or negative. We've got real values, which are 32-bit floating point values, and then we've got long real values, which are 64-bit floating point values. Basic arithmetic functions can all be used for all these data types. Some advanced functions, like the logarithmic function, can only be used with real and long real data types. We'll start with a simple integer math function. I'll add a couple variables together. We'll start with integer variables. I'll pull them off of this list here. I've pre-configured a couple of variables, variable 1, variable 2, and then a variable called sum. So we have a simple math block adding these two values together. We're going to get a lot more advanced than that. Let's say we want to create an average. We're going to add the values together, and then we need to divide by the number of values. So one option we have is to cascade functions together. So I'm going to add a divide function here. We'll start out with our sum, and then we'll divide that by the number of samples. Then our answer is going to be a variable called average. So this is how we cascade together function blocks. We know that every value here cannot exceed 32,767 for integer math. If that integer value is exceeded, the function block will not pass power. If we're dividing by 0, we'll have an error here. You can flag an issue with a function block by putting a contact or a coil at the end of the rung. Then, if you have a problem, it will be flagged. Okay, now let's do the same calculation, but this time, let's do it in an expression. Okay, so I'm going to create a new rung, and this time I'll use the math expression block. I'm going to drop an always on contact here, and then I'm going to right click and select new rung. I'll go into the math expression block. You can select your data type here. We are using integer. We type in the equation here. We can do something like this average, and I'm using variable names. Now I want this to be executed in the proper order, so I'm going to ensure I have parentheses in here. Okay, now when I hit OK, I'll get an error. Expression must start with a memory reference, okay? This only applies to register-based advanced ladder, not variable-based advanced ladder. With register-based ladder, you have to start a math expression block with a memory reference. So I can't type in average for the result. I have to type in the memory reference. In this case, average is %R5, so I'll type that in. Okay, so those were the basic math functions. Now let's look at some of the advanced math functions. We don't have integer equivalents of the advanced math functions, at least from the standpoint of the logarithmic and trigonometric stuff. With advanced math, you only have real type functions available. Let's look at what happens if we do a calculation with a mixture of different variable types. Let's say we have an integer and a real value that we want to average. We have to make sure all the variables are of the same type, and that's where conversion operations come into play. I'm going to use one of these conversion functions to convert one of my integer variables to a real variable. I can also do it the opposite way around, converting a real variable to an integer. Conversion functions allow you to do math on variables that are starting out as different types. Let's load up a program that is using advanced ladder with tags, or variable-based advanced ladder. Let me arrange my screen a little bit here. When you're programming your logic in advanced ladder with variables, instead of getting all your variable names handled by the IO name tool, we have this program variable window instead. Before we dive into the specifics of this example, let me show you this math expression block. With advanced ladder with variables, you aren't restricted to having a memory location at the left side of the equation. Everything in here is variable based, which makes it simpler. When you're using the math expression block, you are limited to 160 characters, regardless of which language you're using. So if you've got really long variable names and a complex algorithm, you could run out of space in your function. Most of the time, you won't have to worry about that though. Now I'm going to switch to my controller and show you an example. I've created a couple of examples showing that it's practical to use logarithmic and trigonometric functions in a real application. I'll show you those now. Let's say we have an application where we have a large object and you want to be able to measure the height of it. I'm showing a tree here on the screen. You could use the tangent function as an example, in combination with an inclinometer and a laser sensor that measures horizontal distance. If you know the angle from the ground to the top of the tree, and the horizontal distance from the laser sensor to the base of the tree, then using the tangent, you can calculate the height. So that's an example. Let me show you how we're programming that with advanced ladder with tags. Okay, so our calculation is the horizontal distance times the tangent of the incline angle, equaling the height of the tree. Now for all the trigonometric functions, the angle is always expressed in radians. In this example, before this math expression block, we have a degree to radian conversion function, so our angle that's on screen has been converted to radians. Okay, so we have a degree to radian conversion, and then we do a simple tangent conversion. We'll look at our application again. If we adjust the angle, it'll affect the height. Let's say it's a 70-degree angle instead of a 55-degree angle. Now our tree is much taller. So that's an example of a simple application using a trigonometric function to handle the calculation. Let's say we want to do the same calculation in our IEC languages using structured text. I'll open another program here. It has the same math calculation, but using structured text. For IEC users, structured text is a fantastic option for doing math functions. It's great for string handling and math. Let's look at what we've got here. We need to convert our incline angle from degrees to radians. We have a syntax here of the incline rads variable, so that's the incline angle in radians, and then we do a degrees to radians function on the incline angle, which is a real function. In the next step, we take our object type and set that equal to the horizontal distance times the tangent of our incline in radians. Okay, so that's an example of how structured text does math functions. If you're unsure about the syntax, you can drag any of these functions onto your editing area. I'll drag the absolute value function over here. Let's create some open space. There's the syntax for the absolute value function. It's ABS inside of brackets, and your variable can be any data type. If we look at the log type, for instance, that has to be real. So those are some simple examples of using structured text for math. Now, just like in ladder, you need to make sure that all of your variables are the same type. I'm going to delete this here, and now I'll show you an example of a simple math function that we might use a logarithmic function to solve. Let's take a look at our logarithmic function example. We have an object that starts at a certain temperature. We'll put it into an oven, and we'll heat it up to a final temperature. We'll use Newton's law of heating and cooling to solve for the heating time. Let's say we started at 40 degrees Fahrenheit. We want to finish at 165 degrees Fahrenheit. We want to know how long that's going to take, depending on the oven temperature and the material coefficient. Newton's law of heating and cooling uses the natural log to make that happen. You can see the formula for that at the top of the screen there. In this case, we've calculated 2.9 hours of heating time to take this material from an initial temperature of 40 to a final temperature of 165. If we adjust the oven temperature to 400, the heating time has gone down to 2.7 hours. Let's take a look at how we would do this calculation. Let's start with structured text. So this is my heating calculation. With structured text, I can do it all in one fell swoop here. So I've got my heating time variable. It equals -1 divided by my material constant times the natural log. This is where we take our differential between our oven temperature and our final temperature divided by our oven temperature minus the initial temperature. We take the log of that and we get the heating time. Let's look at advanced ladder and see how we would do that. Okay, so here's our logarithmic calculation. We were able to write the whole thing out except for the result, which is a memory location. Hopefully that'll give you an understanding of the advanced math function. Last thing I will cover are scaling functions. So I'm going to go under advanced math and select scale. This is a very useful function for taking analog inputs, for instance, and scaling them to engineering units. So I'll create a new rung. It would be illegal if I didn't put a contact here. That's a rule we have with advanced ladder. So now I've got a scaling function. There's a couple of ways to handle scaling. One option that is realistic for a lot of engineering units is to do everything in integers. As an example, let's say my input is coming in analog input number 1, and let's say that this is raw pressure. I'm defining everything as I go because I'm using advanced ladder with register based. Let's say it's values that are coming in from 0 to 32,000, and maybe that's 4 to 20 milliamps. When we're at 4 milliamps, I'm going to have a value of 0, and at 20 milliamps, I'm going to have a value of 32,000. I'm going to pick a general purpose register 100 for a pressure valve, and I'm going to name it pressure PSI. For this particular pressure sensor, my minimum pressure is 10, and my maximum pressure is 100. So I could use the scaling function, and it would work perfectly well. The only negative here is that I'm taking a high resolution analog input, and I'm rounding everything off to the nearest pound per square inch, which isn't ideal. Because my numbers are small, I can add one or more implied decimal points. So 10 and 100 will be represented by a couple of extra zeros here. I will be able to show 10.00 or 100.00 on the screen. I haven't converted those over to a floating point value. I've simply allowed for placing an implied decimal point on my screen. Let's do that now. I'll pull up a screen here. I'll put a numeric object here on the screen, and I'll stick with integer math. I'm going to select pressure PSI from the list, and I'm going to display this as a decimal value. There's no sign involved. Let's say 3 digits to the left and 2 digits to the right. And then I'll put engineering units of PSI in there. I'll make the font a little bigger, and I'll give it a legend for pressure, and I'll make the font of the legend a little bit bigger as well. That gives you an example of how all the scaling that we did stayed as integers. Yet, we're displaying the value on the screen in engineering units, and we never converted from an integer to a real value. So that's one way to do it. However, this way doesn't work for everything, because sometimes you could have potential overflow issues and that sort of thing. Now let's do it another way, where we actually convert the value over. So let me scroll down, and I'll do another point this time. I'll start a new rung here. Now, let's say I'm starting with an integer, but I want to do the scaling in floating point. Well, the first thing I'll do is convert my analog input integer over to floating point. So I'll use the conversion function to convert integer to real. This time, let's use AI2, and we'll call that pressure to raw. And let's convert that to a new value here. We'll call that new value pressure to real. Okay, so I've created a new variable that is the real equivalent of this integer number. Now I can go back and do my scaling function, but this time, instead of doing it with integer variables, I'll do it with real variables. So my input will now be pressure to real. Alright, it still has a minimum of 0 and a maximum of 32,000. I'll just create a new output called pressure to PSI. And again, let's say it's the same scenario with 10 to 100 pounds per square inch. And because I'm using real values, they won't be shorted as integers. I'm going to bring up my screen and I'll copy and paste the pressure sensor. I'm going to have to change some things here to make this work. First of all, This is a 32-bit variable that we're dealing with. It's not a decimal, it's going to be a floating point. And I need to select the proper variable here, which is pressure to psi. I also want to select the proper number format here. We're still going to want to display it in the same way, so I'll select 123.12, which can be hard to find in this dropdown. There we go. We should probably change the legend, but I'll leave that alone for now. Okay, so what I showed you there was two ways of using the scaling block, one with integers and one with real numbers. So that covers what I wanted to cover today. We'll wrap up this demonstration now. Thanks for attending today's tutorial. The Q&A session will begin shortly.
Okay, nice and short this morning. Let's see if we have any questions in on that. I want to use the one equation in multiple instances. Yeah, you can use UDFBs for this. So if you create a UDFB with your equation, you can make as many instances as you need to put this throughout your program. Different programs, it's easily accessible across. I'm not seeing anything else in at the moment. It was straightforward this morning by the looks of it. I will take you now to our webinar page and show you what's coming up. So hopefully you should see my screen now. So next week we do have a webinar on RTD thermocouples and thermistors. Same time as always, and the registration link is there. If you haven't registered already, if you'd like to do so now, that'd be great. Following on from that, you can see what's coming up in the following weeks as well. So we have connecting encoders, we have security, protecting your IP, and getting started with IEC. And always, if you have missed it or you have to dip in and out, we do have all past webinars found below here, so you can access them at any time. That looks to be it for this morning. Thank you for joining us. And again, hopefully we'll see you next week. Goodbye.